All right, let's get started. Let's do the biweekly, today's biweekly. Here's the link. Let me pin it. And let's start with Q1. Let me also share the link. All right, so minimum operations to exceed threshold value 1. So yeah, so here notice that there are two parts of this problem. So you can think that maybe I can do part 2 and then reuse my solution, but it turns out that it's not exactly. So sometimes when problems have many parts, they are the same problem and the only thing that changes are the constraints. So you have to do a fast solution for the second part, and you can get away with a slow solution for the first one. So if you solve the last part, you can reuse your code. But here it's not the case. These are different problems. So minimum operations to exceed threshold value 1. So you're given an integer array nums and an integer k, and in one operation you can remove one occurrence of the smallest element of nums. Return the minimum number of operations needed so that all elements in the array are greater than or equal to k. Okay, so notice here that there's no choice to be made in these operations. Right, so you just have to remove the smallest. So that means that you can just simulate the process, count the number of operations, and that's all you need. Also, the size here, since this one is uneasy, it's only 50. So we can just simulate this. But notice that we don't need to. We don't need to simulate. We know that we are going to remove all the elements that are less than k, and those are the operations. So we can just count that, right? So we go for all the elements in nums, and if they are less than k, then we count 1 for that element. And this should be it. We saw the examples, and that was easy. A short one-liner. Share the submission. Easy. Yeah, I mean, it was well, usually Q1 is easy, but this one has pretty short code as well. Very short. So let's move on to question 2. So now, again, we have an array, integer array nums and an integer k, but now in one operation, we take the two smallest integers, x and y, then we remove them from nums, and then we add this value anywhere in the array. So it seems like we don't care what this is, I think. If we just simulate, return the minimum number of operations needed so that all elements of the array, hey, noob, how's it going? So that all elements of the array are greater than or equal to k. All right. So seems that, like, well, let's check out the constraints. So there are 200,000 numbers at most. So we can try to simulate it, but we have to be quick on each iteration. So on each iteration, the numbers decrease by 1 because we remove 2 and we add 1. So if we do the simulation, we're going to have as many iterations as numbers, or maybe less, but in the worst case, we're going to have as many iterations as the number of elements, -1 or something. Hey, smart coder, welcome. But notice that what we need to do quickly is to get the two smallest elements, the two smallest integers, and then we have to insert a new element. So whenever you have a data structure where you have to get the smallest value and you want to get that quickly and then remove it and then insert another element, you should think about a heap data structure. It offers both operations in logarithmic time. In Python, we already have a module that implements a heap, so we can try that. So first, we're gonna so a heap is just an array that satisfies some conditions. So in heapq, the module of heap for Python, you already have a heapify function that turns any array into a heap. It makes a heap. So and it's a mean heap, which is what we want. So then we're gonna count how many operations we do, and we want to keep doing the operation while there is at least two elements, and the smallest, which is going to be in the at the beginning, is so all the elements are greater than or equal to k. So if the minimum is less than k, then we keep going. Right? So now we get the two minimums, so we pop from the heap twice, and now we want to push to nums this value that, remember, we don't care about it, we just heapify is in place, right? Yes, it modifies the order of nums so that they satisfy the heap condition. So remember that we just copy pasted. We don't care what it is. It's just any value. It doesn't matter. And here we count this operation and we return. And so there's only no, there are more than. Why am I getting only one? Oh, there we go. 2 and 4 looks good to me, and accepted. Big IQ way? I don't know. My way is kind of it's not smart. But let's not get ahead of ourselves. Can you explain how heap works internally in detail? Oh my goodness. Yeah, so a heap is just a binary, a complete binary tree that is represented as an array. So you have a binary tree, but when I say it's complete, it means that I don't remember. So the last level might be incomplete, but it has to be all the nodes from the left to the last node have to be in there. And the condition that it must satisfy is that the heap condition is that it's a recursive condition. So for this subtree, the whole subtree to be a heap, the left subtree and the right subtree must be heaps, and the value of the root must be greater. Well, depends on if it's a mean heap, it has to be less than or equal to both. You know how heap works? Yes, of course. So how do you represent this as an array? So here we have 6 nodes, so we'll have an array of size 6, and so here in this case we use it's useful to do one based. I don't know how they do it, but so here we're gonna have, so if you are at node I, which is represented by these indices, then you can get to the left child as 2i, 2i, and then 2i plus 1. So for example here, if we are, so notice this is node 1, 2, 3, 4, 5, 6. So if we want the left child of node 2, it's 2 of I. So 2 times 2, which is 4, and then 2 times 2, which is 4 plus 1, we get the right child. So I'm not going to dive, so I thought it was very similar to seg3. Well, not really. It's a different thing. So here, so in seg3 you have, so the leaves of the tree represent the array, and then the inner nodes of the tree represent aggregations of the array. But in the heap, every node is an element of the array. So this is a heap, so R here is going to be the minimum element. And then when you there's an operation for if you have an element. So yeah, maybe I shouldn't go too deep on this. So you can find any well, you can watch a video. What if the array is 0 based? So I think it's just 2i plus 1 and 2i plus 2. Or I mean, you can always translate from 0 base to, from 1 base to 0 base, so it doesn't matter. Okay, so yes, I'm not gonna dive too deep into this. I can do another stream about it if you're interested. Can you explain how a heap keeps the max or mean property at root? So there are two operations that modify the heap. So one is when you remove the minimum, and what you do when you remove the minimum is to move the last element. So you remove this and you move the last element to the root. So now this is not here, and then you have a procedure for reestablishing the which is sometimes called heapify. So Python is kind of a misnomer, the heapify. But what you do is you compare. So you know that this is a heap, and you know that this is a heap, but you just added an element here that might not satisfy the heap condition. So you compare it with this and with this, and you put the minimum of all of the three here. You move it to the root so that it satisfies the heap condition, and then you recurse to the one that you swapped with. And again, you're at the same situation where the root might not be the minimum, and you keep doing that until you reach the end. So that's why it is logarithmic, because you go down only one path of the tree. So the order is the height of the tree, which since it's a complete binary tree, it's the logarithm of base 2. All right, so let's move on to the. So I recommend reading the CLRS book for a very good introduction to heaps, to the heap data structure. I guess you can also watch some YouTube videos. There are probably lots of them. So let's move on to problem 3. So count pairs of connectable servers in a weighted tree network. So you're given an unrooted weighted tree with n vertices representing servers numbers from. They're not coach certified. So if there is interest, I can do an introduction to. I mean, I do certify CLRS. That's one of the best sources for learning DSA. But sometimes it could be a little hard to follow. Could be too mathematical. But if there's interest, I could do an introduction to heaps, but in another, so the internals of heaps, but in another stream. Let's keep this focused on this for now. All right, so we're given a tree, an unrooted weighted tree, and we're also given an integer signal speed. And two servers A and B are connectable through a server C if so. Okay, so these are two nodes that are different than C, and distance from C to A is divisible by signal speed. The distance from C to B is divisible by signal speed. And there are no shared edges between the paths from C to B and the path from C to A. Okay, return an integer array count of length n, where count of I is the number of server pairs that are connectable through the server I. Okay. And notice, this is very important. The number of nodes is up to 1,000, right? So that means instead of like 10 to the 5. So that means that we can get away with a quadratic algorithm. I feel like Chris. So Sierra LRS CLRS. Yeah, I mean you don't have to read it all. I mean, it's a reference book. So for example, now you want to learn about heaps. You can try to follow that section of the book. I mean, you can skip the proofs. Maybe no understanding the proofs might be out of scope. Depending on what you want. So I mean, in any case, the first thing that you need when you encounter a new data structure, the first thing you need to understand is its interface and its guarantees. Its guarantees in terms of complexity. Because and you can already use it if you know that clearly. You can already use it as a black box, right? So for example, to solve this problem, if you know the order of complexity of all these three operations that we're doing, then you can use it without knowing the internals. So I think that's the first step, and with that you can solve a lot of problems. You know, and the internals, they are more for when you have, for example, yes, I would say the interface. The internals, you need the internals when you have to do something more. You have to do some kind of modification, or well, maybe your interviewer will ask if you have a notion of how it works internally. Okay, so going back to this, so this is important because it means that we can do an n-squared algorithm, and here there's a very natural way of doing an n-squared algorithm, because we have to return an array of length n, and for each I, which would be the c here, so we want to count connectable pairs that go through server I. So we can do some kind of traversal, some kind of linear algorithm for each I, and that's going to run in time because of the size limit. So yes, notice that if we so let's say that we consider the tree rooted at I, where I is the node that we are considering as the middle point of the path. So this is the root, and so we're gonna have subtrees here. It's not binary, right? So it can have many children. And so notice that the paths, let's draw 3 children so that it's clear that it doesn't have to be binary. So we want to consider paths that go through I, right? And so, and the condition, notice that the condition is it's applied independently for each path to I. So if we're, let's call this C. I like the C. So let's say that we have A here and we have some node B here. So we can consider the path. So we have a path that goes through A, goes to A, and here we have a path that goes to B. So what we are asked to consider is the path weight or distance. The sum of the weights of this path has to be divisible by signal. And so, and then all the other conditions are going to be satisfied, because since we are going down to different trees, to different children, subtrees, then they won't have any edge in common. So what you need to understand here is that we can find all the nodes that satisfy this condition by traversing all these subtrees, and then we just have to count the combinations of them. When we count the combinations, that's going to be all our pairs. So notice that, so if we have like 3 nodes here that have the condition that the path is divisible, and then we have 2 here, then we have 3 times 2 pairs, right? We can connect this one to this one, this one to this one, this one to this one, and then the same for this one. So we have to multiply. So we just have to count how many of these valid nodes there are from the top, and then we just multiply to count all the pair combinations. Okay, so we have the number of nodes is 1 more than the number of edges, because this is a tree. Then in order to traverse the tree from a given node, what category of concept does this? So it's a little bit of, well, trees by tree traversal, then a little bit of combinatorics, because we have to count the combinations. Now I'm going to explain how we do that, and maybe a little bit of graph theory for representing the adjacency list, because in order to traverse the tree from any root, we need to create an adjacency representation of the tree. So this is how we do that. We go over the edges and we add an edge. This is not directed, so we have to add the edge both sides. So now we have an adjacency list representation, and so we want to count. Let's call this count. We want to traverse a subtree, and we want to count how many nodes have this property of that the path from the root is divisible. The sum of the weights of the path from the root to the current node is divisible by signal speed. So how do we do that? So we're going to traverse. We are at node U. The parent is going to be some p, so that we can traverse it without without revisiting nodes. We have to remember which is our parent, and then we want to keep track of the distance, the sum of the weights, so that we count. So we're gonna consider node U. If the distance is divisible by the signal speed, then we want to count 1 for this. We want to count this node. Otherwise, we don't count it. And then we go over the children, and we want to avoid going back to the parent, and then we count how many there are from the child, and now the parent is going to be u, and the distance has to be, we have to add the current weight, the weight of the edge. So this is going to count all the valid paths or nodes. And so now we want to return the list. So we're going to consider every node as the root. And so we want to handle the root here. So we want to go over all the children of the root, because these are the ones that we considered here, right? So, and we want to count, we want to call count with b, and the parent is going to be the root, and the weight so far is going to be w, the distance so far. And now notice that we have to keep track of all the nodes that we've seen to the left. The paths don't collide. What do you mean by collide? Having sharing edges. So since we are making sure, okay, so for paths to not share edges, they have to go over a different subtree, because if they were part of the same subtree, then they would share this edge, the edge that goes from the root to that subtree. So by combining nodes from different subtrees, we make sure that's a sufficient and a necessary condition to count all the pairs. Okay? So now I'm going to explain how we count this. So we're gonna keep track. So we're going from left to right to the, well, in some order, it doesn't matter, to over all the children of the root. So we're gonna keep track of how many we already visited, right? How many nodes were on all the subtrees to the left of the current one. So in order to keep track of that, we're going to add the count of the current subtree. And now we want to keep track of all the pairs. So yeah, let's call this pairs. Hey, Creepypasto, how's it going? Nice to see you. Okay, so here the pairs we want to add. So this is how many there are on the current subtree, how many paths, how many nodes, and then we want to, all the ones that are to its left can be paired with. So we multiply this, and then we append the pairs for this root, and this should be it. And we have the right accepted. Okay. So this is a common pattern where when you're counting pairs, you go from left to right, you count how many there are in the current, and you pair them with all the elements that it can be paired with, that you already processed. Hello, Octa, elliptical. All right, so this one, I don't think it was, so in the end you have to do a traversal of a tree and do some counting. I think it was the right difficulty for a Q3. Made sense. So let's go to question 4. All right, find the maximum sum of nodes of node values. There exists an undirected, so we are given again I saw someone doing this question today, Q4. That's cool. Okay, so we're given again a tree, but in this case it's unweighted. We're given the edges, and we're also given a positive integer k and non-negative integers nums of length n. So nums I is a number associated with each node, okay? And you want Bogdan wants to sum the sum of values of the tree to be maximum, for which Bogdan can perform the following operation. Python. My solution is not long. It's short. It's shorter than this one. But I think it's a little more complicated. Okay, so we can perform this operation any number of times, including 0, on the tree. So we choose any edge, and we XOR the value of nums of u, and so we update this with the XOR of k. Okay, so return the maximum possible. Okay, so just and we have 200,000 nodes in the worst case. All right, so just a few observations first. So notice that if we apply this more than once, so remember the XOR. There's a condition that comes up a lot, which is that x XOR x equals 0, and any x XOR 0 equals x. So these two properties you should know. So notice that if we apply num of I, and we do the XOR k, if we do that again, then this will cancel out, because this is going to be 0, and XOR to 0 is going to be the nums of psi. So that means that it doesn't make sense to choose an edge more than once. You either choose it 0 times or 1 time, okay? 20k, what? Oh, the constraint was 10 to the 4 or 10 to the 5th? Oh, 10 to the, oh, you're right. Yeah. Well, in any case, you usually don't, though this means that you cannot do something quadratic. So I know that there was an exception here in the heap problem. So you noob, you were able to you were able to solve it with an n squared solution. So good for you. I think that was not intended to pass. I don't know. Okay, so we said that we want to choose an edge either 1 or 0 times. So that means that maybe we can do dp. So at take it or leave it dp, where for each edge we have two options. We either do the operation or not. Yeah, there's some corruption there, maybe. Okay, are you bribing LeetCode? Anyway, so there's a quote that says, "Never attribute to malice that which can be adequately explained by stupidity." So I think this is a mistake from LC. DP on trees is tough, otherwise it's all right. So yeah, here it's a little trickier. At least this is what I did. I don't know if there's a simpler way, but so here we're gonna be doing a traversal by edge. Okay, so first, like we did before, we're going to create the adjacency list to traverse the tree. And then we're gonna have a cached function. This is where the p comes, which is going to give us the max value from starting from some node. We're at some node u for some parent, which let's say that for the root is going to be -1. It's just some value, and then this is going to indicate which child we are on, because this is going through the edges, not the nodes. So we need a node and a child. This is going to define the edge, and then we are going to remember if we already selected the operation of the edge that leads to the current node, and this is going to be initially 0. So when we get to the end of the children of u, then we just return. So now we know how many edges we selected that are connected to u. So that gives us that's going to tell us if we have to XOR it with k or not. So every time we select an edge that is connected to u, we toggle this number, right, the q, because if it's odd, we're going to do the XOR, and if it's not, we're not going to do the XOR. So we're trying all possibilities. Okay, now we need to check if the current child is the exparent, in which case we just want to skip this child. And here's when we have the take it or leave it part, right? We want the maximum of, and here let's say that we don't take it. So if we don't take it, we want the max value of the child of u. Now the root would be the parent is going to be u, and we start from the first child, and we haven't taken this edge, so the number of edges that we selected are 0. And then we continue. We get also the mat value going to the next child of u, without adding any other edge that we selected. Okay, and now we're going to do something similar, which is when we leave it. When we take it, when we choose this, then here we have to add 1, because the edge that goes to the child, it's going to be selected. We are selecting it, and here we also have to count the other end of the edge. So we toggle Q, and that is it. Yeah, this is like I said, so the code is pretty short, but it's a little bit harder to follow if you don't because we're doing a traversal from edges. So NCC. So I don't think this was the big brain solution. I think this is just DP via edges. You can XOR any two nodes because you XOR the edges in the path. I'll have to think about that. No, I'm not gonna do another solution on stream. I'll think about that one. All right, so yeah, when you find a DP solution, sometimes you can. So sometimes I say that DP is dumb in the sense that you don't have to be clever, and so you in DP you are trying all the possibilities. You don't have to be smart and figure out some greedy choice. So there's nothing to prove when you're doing DP. So yes, let me share my solution. And yes, that's all I got. That's all I got. So thank you for your support. and see you in the next one. You mean this one, the Q4? Thank you. Thank you, thank you. So did you solve it? Run it back 6 hours, so you think they will change the system tests or something like that? We knew oh. Oh, okay. Yeah. Probably. So I'll probably do a stream tomorrow of the contest. If I like it, if I can solve them all, I'll do another stream tomorrow. But yeah, I gotta go now, guys. Sorry. See you in the next one. Bye bye. Thank you.